Hello, I am Federica Ciuffo. I'm a specialist solutions architect for container technologies at Amazon Web Services. Today, I'm going to talk about how the Kubernetes ecosystem has evolved to answer to more complex application patterns from a networking standpoint. So let's dive right into it. Let's start with the easiest pattern, which is the monolith. How do we handle internal calls and client traffic within the monolith? Well, applications are on the same physical and virtual machine into the monolith. Therefore, we use loopback interfaces to grant communication. And how do we handle client traffic? Well, if you want to be fancy, you can use a load balancer or a proxy. But this pattern, the monolithic one, is not used anymore because of a number of reasons, as reducing dependencies between applications, enabling developer flexibility, reducing blast radius, and decrease time to market. So we broke down, or a pattern that is very common is to break down these monoliths into microservices. In particular, you can containerize those and manage them with, for example, Kubernetes. So in the Kubernetes context, how do we handle service-to-service communication? Well, when you containerize your application and put this into a Kubernetes cluster, your application will talk thanks to the container network interface. Some examples include Amazon VPC CNI, Cilium, and Calico CNIs. And well, client traffic can also be handled by load balancers, but when we are talking about application traffic, Kubernetes ecosystem is something more. And this is actually the ingress resource that needs deployed into your cluster, and an application, which is the ingress controller, which picks up the creation, update, or deletion of ingress Kubernetes objects and automatically creates, updates, or deletes load balancers. Well, of course, breaking down your application into microservices is only the first step. The pattern that we see with our medium, large-scale customers is to further break down applications into different clusters or different areas of the cloud to gain flexibility, enforce separation of duties, and security. Well, so let's recap this a little bit. You have multiple microservices which are spread across different clusters, different areas of the cloud, and those are written in different programming languages usually. So in this context, how do we handle service-to-service communication and client traffic? Well, we need to take into account some challenges. So first of all, how do we manage network connectivity and traffic routing? And how do we obtain visibility into service-to-service communication? Let's say, how do we manage the observability of my systems? And how do I ensure trust by automatic security and compliance in my systems and applications? Also, tied to the modernization of our application patterns and architectures, we need also to modernize our organization and really create a culture of innovation by organizing, well, our teams into small DevOps teams. So those objectives needs to be taken into account, or were taken into account from the Kubernetes ecosystem when deploying more advanced offerings and answers to application networking in Kubernetes. Let me introduce a couple of concepts from Amazon Web Services. The first one is Amazon EKS, Elastic Kubernetes Service. This is a managed Kubernetes cluster from AWS in which we manage the control plane of a Kubernetes cluster. In the slide, you can also see Amazon VPC, Amazon Virtual Private Cloud. It's basically a chunk of the AWS Amazon network that we give to you and that you manage completely. Resources like Amazon EKS live in an Amazon VPC. So again, how do we set up and manage the ingress and service-to-service communications while guaranteeing agility, control, visibility, and security? Well, you could use, again, load balancers, but planning for scale, you don't want really to provision and manage a load balancer per service. There are techniques with ingress controllers that enable you to, well, share load balancer across multiple applications, multiple backends, but still, when your application scales massively or when you have stricter requirements, you may need to adapt. Let's recap. We have seen how networking is handled in monolithic applications, how Kubernetes answered to containerization with CNIs and ingress controllers. So let's talk about now how microservices are handled by the Kubernetes ecosystem and how the networking offering has evolved to answer to the problems of having a distributed system. Well, Kubernetes project said, okay, proxies are really useful to manage networking in general. Why don't we use them within a Kubernetes cluster as well? In fact, there is a pattern which is called to put this proxy as sidecar within the same pod, sidecar to my container that is next to the container which handles the application, and put these in each pod that I have in my cluster. This pattern is known as sidecar proxy pattern. And it is basically a way to decouple the networking and the application layer. All the traffic that needs to go into the application pod or container or generates from the application container passes through the proxy. This enables us to have, let's say, more flexibility between our applications teams. Let's say that we have a team that manages a front end and that needs to talk with a team that manages a backend. When the backend team releases a new version, we need to actually change and put our application code in the front end and point to the new backend. Well, this is not needed anymore if we are using a proxy as sidecar, because we can actually use the proxy to point to the new application. So inconsistencies are minimized. We are separating, let's say, business logics from operation, and also operation of installs, upgrades, etc. are a little bit more easier. And well, again, one of our objectives was to make our application observable. Now we have a unified layer, one of the proxy, that manages our service-to-service communication and that gives logs which are in the same programming language. And in the same way, because it's actually the same proxy next to each container of our application. This adds a layer of observability that is very important when we are managing sidecar or application at scale. But again, we are talking about scale. How do we manage all of these sidecar? Well, much like in a Kubernetes cluster, we manage our applications with a control plane. And well, think about having a control plane also for our sidecar proxies. And the control plane plus the data plane, which are the sidecar proxy themselves, it is a service mesh. On the left side of the slide, you can see some examples of service meshes which are commonly used by our customers. Let's dive a little bit deeper into use cases. Well, obviously, traffic routing is something that we want to manage with a service mesh. For example, routing from a version 1 to a version 2. But also there are some advanced features for routing, like for example, prefix and query parameters, or specifying HTTP headers. Let's say that we want to protect also our application from large spikes in traffic, and we want to assure a good level of services. Well, the service mesh enables me to implement automated retries, secret breaking, and rate limiting into our applications. Security is also one of our objectives, and you can enforce that your application are able or not to talk either within themselves or among themselves or to third-party APIs. You can also enforce that the communication are encrypted, and so enforce TLS, for example, at the reverse proxy level, not at application level. This can also integrate with third-party services to generate and renew certificates. Not only TLS, but we can also enforce service-to-service authentication with mutual TLS. Another use case is observability. We talked about it a little bit, but basically the layer of observability that I gain is that I can also implement a tracing within the proxy to understand upstream and downstream dependencies. And also I can understand where the bottlenecks are and identify patterns and understand service performance. Another common use case is multi-cluster. So connecting together different clusters which are placed maybe also in different VPCs or different accounts. And the communication can be granted by implementing in the correct way, obviously, a service mesh. One common proxy that is used within meshes is Envoy, which is basically highly performant cloud-native proxies. It's very efficient, it has a really small footprint, and it handles, well, client-side load balancing, retries, timeouts, rate limiting, enables you to have observability at layer 7 traffic, and supports different, for example, HTTP, HB2, CRP, and TCP protocols. And also, it has rich and robust APIs for configuration. One service mesh that uses Envoy proxies is Istio. You can install Istio into your cluster using Istio-CTL or Istio operator. Create and manage the components like, for example, mesh, virtual service, virtual gateways, etc. through Istio-CTL and Kubernetes APIs. There are different supported platforms on Amazon Web Services. You can configure and run your mesh in Amazon EKS, Amazon EKS Fargate, self-hosted Kubernetes on Amazon EC2. And also it integrates with Kiali. Kiali is a console for Istio Service Mesh, and you can use it to configure, visualize, validate, and troubleshoot your mesh. Let's see how it is Istio deployed into our cluster. We have an EKS cluster, we want service A and service B to be able to communicate. So when you deploy Istio, we are actually deploying the data plane, which are, again, the proxies throughout the service flows, and the control plane. The control plane is, a set of pods, which is Istio-D, and it's not managed by AWS. It lives into the clusters as a resource pod. So Service meshes is really the answer to a lot of our challenges. But, well, still some remain. We have a lot of now sidecar proxies that we have to deploy and maintain. At a scale, this can be challenging. It only integrates with container-based workloads. Let's say that we are using, let's say, a serverless service like AWS Lambda or Amazon EC2. This is not really supported. And also, before even thinking about deploying a mesh, we need to have inter-VPC networking that we need to actually implement to grant connectivity across VPCs, for example, and to enforce security. So how can we answer to these challenges? Well, let me introduce the Kubernetes Gateway API. The Kubernetes Gateway API is a SIG network project that took the lesson learned from the Ingress project and implemented a new way of doing networking into Kubernetes. We have different objects that belong to the Kubernetes Gateway API. The first of it is Gateway class. The Gateway class enables me to formalize basically the type of load balancing implementation that I can use. Let's say if it were an Ingress, for example, it would be a load balancer. The gateway actually specifies a point where the traffic can be translated into the Kubernetes services. So how do I translate traffic that is coming from outside the class inside the class, and where this is? HTTP routes. Those are rules for mapping the request from a gateway to Kubernetes services. And the services are basically the targets of our HTTP routes. A nice feature to the Kubernetes Gateway API is that it is role-oriented. And we have finally a mapping between the Kubernetes objects that we have in our cluster and a role within our organization. There are different implementations, like for example for the Ingress, we have different Ingress controllers. So we have different controllers for the Kubernetes Gateway API. You can recognize different icons that we have already seen in our presentation, like for example Istio, Nginx, HA Proxy, and a new one. This is the Amazon VPC Lattice icon. Amazon VPC Lattice is a networking service that we have in preview and announced in our previous re:Invent 2022. And basically this implements a layer 7 fabric with layer within the application VPC fabric. So to say, we can enable service-to-service communication without sidecar proxy, which are required, and much like a service mesh, but without the need of deploying sidecars. It works across all the compute options, EC2, KIAS, ECS, Lambda, and enables you to deploy complex security, let's say, architectures, because actually it's really easy to grant or implement the networking also across VPCs and accounts where before you needed, for example, to deploy transit gateway, pin connections, etc. Let me give you an overview of Amazon VPC Lattice components. We have a service network, which is basically a logical boundary that you can define across VPCs and accounts. And it is used to apply common access and observability policies. Then we have service. The service is a unit of applications, and it extends across all the compute, instances, containers, serverless, etc. We have then the service directory, which is a centralized registry for all the services that are registered into Amazon VPC Lattice. And then we have security policies, which are identity and access management declarative policies to configure access, observability, traffic management, and those can be applied at a service, a gateway, and or application or network level. Amazon EKS supports Amazon VPC Lattice, and we actually have built a controller that when we create Kubernetes Gateway API object, automatically the controller works and creates, updates, and deletes Lattice resources. Let's see a little bit deeper how the controller works. So we have, for example, an object like the gateway, which is deployed. And the gateway automatically will, once deployed, the controller will automatically create a service network and associate the VPCs where the EKS clusters live into the service network. That is, now we have network connectivity between the two VPCs that you can see in slide. Much like as if we had configured, like, for example, a transit gateway and attached the two VPCs to it. Another thing that you need is that, well, now we have connectivity networking that is set up, but we have not defined how the traffic flows. To do so, we need an HTTP route resource. An HTTP route will automatically, once applied, create services, which are again the targets, the unit of applications that are defined for Amazon VPC Lattice. In this case, we have defined two services. One it is local to our cluster, and one which is another service which we actually exported and imported from one cluster to another. That is to speak, let me grab a pen. This HTTP route will be applied, for example, in the first cluster as a resource, and we will have exported and imported this service into this cluster so that it is visible to be picked up from the HTTP route. Then there are other things from the HTTP route. We specify the gateway, which is tied to. So basically, we are associating our services to the service network. And again, we also specify how the traffic it is redirected from the gateway to our targets, which in this case are these two services, one from the first cluster and one from the other cluster. So you can see how now we have granted in a really easy way, easy setup, cross-cluster communication without even needing to set up underlying, let's say, networking components like transit gateway, VPC peering, and then deploying a mesh and deploying and maintaining a set of sidecar proxies. Thank you. I hope this session has been useful for you to understand a little bit better the ecosystem that we have within Kubernetes, and in particular within the answer or integration from Amazon Web Services to the Kubernetes ecosystem, in particular the Kubernetes Gateway API.